Let's take a journey. Today, we're diving into the elegant and powerful world of complex integrals. We're going to be using the classic text from Churchill and Brown as our map, and you're about to see how shifting our perspective from a simple line to a two-dimensional plane, well, it changes absolutely everything.
So, let's kick things off with a simple question. We all get how to move along a number line. You go forward, you go back. But what happens when our world suddenly gets a whole new dimension? The imaginary one. How do you travel? And more importantly, how do you integrate in this brand new two-dimensional landscape? To really dive in, we first have to make a huge shift in how we think. We've got to move beyond that familiar one-dimensional number line and step into the two-dimensional complex plane.
So on the left, that's the world of basic calculus, right? Integration is usually about finding the area under a curve, along a straight line, the x-axis. Pretty straightforward. But on the right, whoa, we're in the complex plane now. Here, our journey isn't just left and right. We can go anywhere, up, down, diagonally, even in loops. And that freedom completely rewrites the rules of what an integral even is.
And that brings us to the hero of our story, the contour integral. See, in this new world, it's not about the area underneath something, it's all about the path we take through this new landscape.
So what is it really? Well, a contour integral is just a way of adding up the values of a complex function, but, and this is the key part, it's along a very specific path, or contour. The path itself is now a crucial piece of the puzzle.
This is the notation you're going to see. Now, it probably looks familiar, but that little c tucked under the integral sign, that makes all the difference. Let's break down what each piece really means, conceptually.
Okay, think of this like you're on a hike. That integral sign, the integral, that's just telling us, hey, we're summing stuff up. C is our trail, the specific path we're hiking. F of z, you can think of that as the terrain, maybe the elevation or some other value at every single point on our trail. And dz, that represents each tiny little step we take along that trail. We're just adding up the value of the terrain for every single step of our hike.
And this right here, this highlights the single biggest, most mind-bending difference from real calculus. On a number line, going from A to B is just going from A to B. The integral is always the same. But on the complex plane, the journey itself matters. As you can see here, taking path C2 could give you a completely different result than taking path C3, even if you start and end at the same places.
This whole idea that the path matters leads to something, well, it's profound. It's almost magical, actually. It's a discovery about the surprising power of the number zero. As Churchill and Brown write in the source text, this theory is known for its mathematical elegance. And they are not kidding. This next idea is one of the most concise yet powerful ideas in all of mathematics. It's just beautiful.
Okay, so let's set up a new kind of journey. Instead of going from some point A to a point B, what if we take a round trip? What if we follow a path like C1 here, a closed loop that starts and ends in the exact same spot?
So what do you think? If we hike all the way around a loop and end up right back where we started, what's the total value of our integral? You might think it depends on the shape of the loop or how big it is, right?
The answer, and this is just astonishing, is 0. This is the Cauchy-Goursat theorem. And what it says is that as long as our function is analytic, which is just a fancy way of saying it's smooth and well-behaved, with no weird jumps or holes inside our path, then the integral around any simple closed loop is precisely 0. It's an unbelievably simple result with absolutely massive implications.
And that amazing result leads us right to the climax of our whole journey, a formula that seems like it has to be magic. It's called the Cauchy integral formula, and it's basically a mathematical superpower. Now, don't get intimidated by all the symbols on the screen. Seriously, we're not going to focus on the mechanics of the formula. We're going to focus on what it tells us, because what it tells us is one of the most profound ideas in all of math. So here's what it really means. The value of a function at any single point inside a closed loop is completely and totally determined just by the values of the function on the boundary line of that loop. Let that sink in for a second. That's like being able to know the exact height of the tallest mountain on an island just by sailing around its coastline and taking some measurements. It's wild! All the information about what's going on inside is somehow encoded on the outside boundary.
Of course, these beautiful, elegant rules all depend on our function being well-behaved. But what happens when it isn't? What happens when our perfect map has these weird spots where the rules just break down? Well, we call those singular points. Specifically, we're interested in what are called isolated singular points. You can think of it like a single lone point of misbehavior in an otherwise perfectly smooth landscape. It's like an island of chaos where our function goes haywire, but it's surrounded by a calm sea where everything is fine.
And these little islands of chaos come in three main flavors. You've got a removable one, which is just a tiny hole you can pretty much patch up, like a missing pixel in a photo. Then you have a pole, and that's where the function just shoots off to infinity, like a volcano erupting from our map. And finally, you have an essential singularity. That's a point of pure, unpredictable chaos, like a swirling vortex. And it turns out, it's around these crazy points that some of the most interesting math happens. So, our journey has taken us from thinking about simple paths all the way to these incredibly powerful formulas. And what we've discovered is that complex integration reveals this hidden, incredibly elegant structure that connects the inside of a space to its own boundary.
And look, this isn't just some abstract game for mathematicians. This elegant structure, it's the bedrock for huge areas of physics. We're talking electromagnetism, quantum mechanics. It is absolutely essential for engineers working in fluid dynamics or signal processing, and it even unlocks these deep, profound truths in pure mathematics itself.
Which leaves us with a final, really fascinating thought. The Cauchy integral formula tells us that a simple, one-dimensional boundary can hold all the information for the entire two-dimensional area inside of it. It just makes you wonder, doesn't it? What other boundaries are out there in our world, in science, in data, maybe even inside ourselves, that hold the complete story of what's inside, just waiting for us to find the right way to see it?
You know, there's a part of mathematics that people don't just call powerful. They call it, well, beautiful. It's complex integration, and it's famous for these incredibly elegant theorems that are surprisingly simple but have these massive consequences. So, let's dive in and see why.
Think back to calculus class. We all learned how to find the area under a curve on a plain old number line, right? But what happens when the world isn't just a straight line? What if you want to measure something not under a curve, but along some winding, twisting path in 2 dimensions? I mean, how would you even start to tackle that? To even begin to answer that question, we need a new place to play. We have to literally move beyond that familiar one-dimensional number line and step into this huge, 2-dimensional landscape we call the complex plane. So to really get this, we need a whole new canvas. Instead of just a single line, we're moving to the complex plane. And as you can see right here, every single point is now a location. It has a real part and an imaginary part. All of a sudden, calculus has this whole new dimension to explore.
And that's the kicker, right? It means our old tools, they just won't cut it anymore. The calculus we learned was built for one dimension. To navigate this much richer, more complex landscape, we're going to need to upgrade our entire mathematical toolkit.
Okay, so how does this actually work? Well, before we can integrate anything, we first have to define what we're integrating along. We need to be super precise about what a path really is in the complex plane.
And that brings us to our first huge term, the contour, or in Arabic, masar. Think of it like a very specific, well-behaved route on a map. It's not just some random scribble. It's carefully constructed from a bunch of smooth, connected pieces.
So the fundamental building block, the Lego piece of any path, is what you're looking at here. A simple, smooth arc. And smooth is the key word. It means no sharp corners, no sudden breaks. It's a perfectly predictable little piece of our mathematical road, and that's absolutely essential for integration to even work.
And then we can build more interesting routes just by connecting these smooth arcs one after the other, end to end. This whole thing is our contour. And even if it has corners where the different pieces meet, that's okay, because each individual segment is perfectly smooth. That's what makes the whole path manageable.
All right, we have our landscape, that's the complex plane. We have our road, that's the contour. Now we need the vehicle that's going to travel down that road and take measurements along the way. And that vehicle is the contour integral.
And there it is. Look at that. Isn't that just elegant? So much power packed into such a tiny expression. So f of z is our complex function. It assigns a value to every single point in the plane. C is the contour, the path we just defined. And dz, well, that represents a tiny, tiny little step along that path, a tiny vector that has both a length and a direction. So the contour integral, or Takaamal al-Masar, does something amazing. It literally travels along the path c, and at every tiny step, dz, it looks at the value of the function f of z and adds it all up.
So it's not just calculating an area, it's accumulating the total effect of the function along that very specific route.
It really all comes together in this kind of three-step dance. First, you draw your path, your contour C. Second, you define your function, f of z, which you can think of as creating a sort of force field all over the plane. And third, you perform the integration to see what the total effect of that field is along the exact path you chose.
Now, understanding the what is one thing, but the real magic, the thing that gets mathematicians so excited, comes from understanding the why. Why is this whole theory of integration considered so beautiful and important?
I mean, don't just take my word for it. The authors of the very textbook we're pulling from, براون and Tshirtshel, they put it perfectly. They say the theory is famous for its mathematical elegance. This isn't just a tool, it's almost an art form. The results it gives are deep, often really surprising, and just incredibly powerful. And this is where the true magic really begins. This theory reveals a shocking relationship between different paths. It tells us that, under the right conditions, the result of the integral is exactly the same whether you take the long, winding outer path or the short, direct inner path. Let that sink in for a second. The specific route you take doesn't matter. This single idea, called path independence, is the foundation for some of the most profound theorems in all of mathematics. Okay, this is all fascinating in an abstract mathematical way, but so what? What's the payoff? Where does this elegant theory actually connect with the real physical world?
This is it. This is where theory becomes reality. That abstract path in the complex plane on the left, that's not just some mathematical curiosity. It's the exact tool that engineers use to model and predict incredibly complex physical behavior, like the flow of air over an airplane wing. The elegant math directly describes the physical world. It's incredible. And the applications are just staggering. This isn't some obscure corner of math. This is the engine that drives modern science. Contour integrals are absolutely essential for designing airplane wings, for calculating electric fields, for understanding heat flow, and even for navigating the super weird world of quantum mechanics. This elegant path leads directly to the technology that shapes our entire world. So we started with a pretty simple question. How do you measure along a path? And it led us to a whole new landscape, a new set of tools, and a theory so powerful it can literally describe the physical universe. It just leaves you with this one final, tantalizing thought. If a simple path can unlock the physics of how fluids flow, what else is out there waiting for us to discover by exploring the complex plane?
أهلا بيكم. تخيلوا كده أن عشان نحل مشكلة واقعية قدامنا، الحل مش إننا نمشي في خط مستقيم، لأ، الحل إننا ناخد منعطف غريب ياخدنا لعالم تاني خالص. هو ده اللي هنعمله النهاردة. رحلتنا هتكون في عالم التكامل المركب، مش مجرد أداة رياضية وخلاص، لأ، دي طريقة تفكير جديدة تماماً بنشوف بيها المشاكل وبنلاقي لها حلول.
وهنا بقى بيجي السؤال الكبير، سؤال ممكن يكون محير لناس كتير. إيه اللي يخلينا نحتاج أعداد تخيلية عشان نحل مشاكل حقيقية؟ يعني إيه العلاقة أصلاً؟ السؤال ده هو محور كل حاجة هنتكلم فيها، وهنكتشف إجابته سوا.
طيب، عشان الصورة توضح، خلينا نبص على مثال عملي. التكامل اللي قدامنا ده، لو حاولنا نحله بالطرق العادية بتاعة التفاضل والتكامل اللي درسناها، هنلاقي الموضوع صعب جداً، يمكن مستحيل كمان. المشكلة إن على خط الأعداد الحقيقية، المسألة دي مقفولة تماماً.
يبقى الحل إيه؟ الحل مش إننا نفضل نحاول بنفس الطريقة وخلاص، الحل إننا نغير منظورنا للمشكلة كلها. بدل ما إحنا محبوسين في خط واحد ليه بعد واحد، لازم نخرج بره الخط ده ونبص على الصورة من فوق، من مستوى تاني خالص، مستوى ليه بعدين. خلينا نفتكر سوا، في الكالكولس العادي إحنا دايماً بنعمل التكامل على خط المحور السيني مثلاً، الموضوع محدود. لكن هنا بقى بتيجي قوة التحليل المركب، بيدينا حرية رهيبة، بيقول لنا مش لازم تمشوا في خط مستقيم، لأ، ارسموا أي مسار يعجبكم في المستوى ده وإحنا هنحسب التكامل عليه. وهنا لازم نتعرف على بطل القصة بتاعتنا، حجر الأساس في التكامل المركب كله، وهو المسارات اللي بنمشي عليها دي. المسار ده ليه اسم بنسميه كونتور، وببساطة شديدة الكونتور ده هو الطريق اللي بنرسمه في المستوى المركب، ممكن يكون خط، دايرة، أي شكل. هو ده الطريق اللي التكامل بتاعنا هيمشي عليه.
وزي ما احنا شايفين، الكونتور ممكن ياخد أشكال مختلفة كتير. بس في نقطة مهمة جدا هنا، الكونتور ده مش مجرد رسمة، لأ، دي رحلة ليها اتجاه. يعني احنا ماشيين منين لفين، والاتجاه ده بيغير كل حاجة في النتيجة النهائية. وعشان كلامنا يبقى دقيق، في كم مصطلح لازم نكون عارفينهم. لما نقول القوس بسيط، نقصد مسار مش بيقطع نفسه، ولما نقول منحنى مغلق بسيط يبقى ده مسار بيلف ويرجع لنفس النقطة اللي بدأ منها من غير ما يقطع نفسه في أي حتة. وأخيراً موجة إيجابياً، دي معناها إننا بنلف عكس عقارب الساعة. دي مجرد أسماء عشان نوصف الحركة بتاعتنا بدقة.
وهنا بقى الموضوع بيبدأ يبقى شيق جدا، لأننا بنكتشف إن قيمة التكاملات دي مش ثابتة، لا دي ممكن تتصرف بطرق غريبة قوي، وكل ده بيعتمد على حاجتين: الدالة اللي بنكملها والمسار اللي اخترناه نمشي عليه.
طيب إزاي بنحسبه؟ دي المعادلة اللي بنستخدمها عشان نحسب التكامل الكونتوري. ممكن شكلها يبدو معقد شوية، بس فكرتها الأساسية هي إنها بتترجم الرسمة أو المسار اللي اخترناه ده لرقم، لقيمة محددة للتكامل.
طيب بصوا معايا على المثال المدهش ده. لو بنكامل الدالة 1 على زد، المسار اللي بنمشي عليه بيغير النتيجة تماماً. لو مشينا من فوق تطلع نتيجة، ولو مشينا من تحت تطلع نتيجة تانية خالص. لكن في المقابل لو بنكامل دالة زي زد نفسها، مش مهم خالص نمشي منين، يمين شمال فوق تحت، النتيجة دايماً هتطلع هي. حاجة غريبة صح؟
وده طبعاً بيخلينا نسأل السؤال المنطقي: إيه الحكاية؟ إيه اللي بيفرق بين الحالتين؟ يعني إمتى المسار بيكون مهم وإمتى نقدر نتجاهله تماماً ونبقى متأكدين إن النتيجة واحدة؟
الإجابة على السؤال المحير ده جت من عالم رياضيات عبقري اسمه أغسطين لوي كوشي. كوشي قدم لنا مفتاح سحري، اختصار مذهل بيحل اللغز ده، وهو يعتبر قلب التكامل المركب كله.
أول جزء من السحر ده هو نظرية كوشي جرسا، والنظرية دي بتقول حاجة تبان بسيطة بس هي في الحقيقة قوية جدا. بتقول لو عندنا دالة مؤدبة أو سلوكها كويس وعملنا بيها أي رحلة مقفولة، يعني بدأنا من النقطة ولفينا ورجعنا لنفس النقطة تاني، يبقى ناتج التكامل ده لازم وأكيد هيطلع صفر دايما مهما كان شكل اللفة دي.
طيب يعني إيه دالة سلوكها كويس دي؟ المصطلح العلمي بتاعها هو دالة تحليلية، والمقصود بيها ببساطة إنها دالة ناعمة سلسة ينفع نعملها تفاضل عند أي نقطة في منطقة معينة من غير أي مشاكل.
تمام، بس ماذا لو الدالة دي كانت كويسة في كل حتة ما عدا نقطة واحدة بس، نقطة صغيرة عاملة مشكلة وموجودة جوه اللفة بتاعتنا دي، زي مثلا لو بنقسم على 0 عندها، هل كده كل حاجة باظت والنظرية دي ما بتنفعش؟
المفاجأة لا، وهنا بتظهر عبقرية كوشي الحقيقية في الجزء الثاني من السحر، صيغة كوشي التكاملية. الصيغة دي مش مجرد حل المشكلة، دي بتكشف لنا سر من أسرار الكون الرياضي ده. اللي المعادلة دي بتقوله حاجة لا تصدق، معناها إن قيمة أي دالة تحليلية في أي مكان جوه المسار المقفول نقدر نعرفها بالكامل لو عرفنا بس قيمة الدالة دي على الحدود بتاعة المسار. يعني كأننا بنقول إن كل المعلومات عن اللي جوه متسجلة بالكامل على الإطار الخارجي. فكرة مذهلة.
ودلوقتي بعد ما شفنا القوة النظرية الجبارة دي، جه الوقت نرجع للمشكلة الأصلية اللي بدأنا بيها: إزاي كل الكلام النظري ده بيحل لنا مشاكل حقيقية في العلوم والهندسة؟
الموضوع عامل زي ما يكون وصف طبخة من 4 خطوات. أول حاجة بناخد التكامل الحقيقي الصعب بتاعنا ونتخيله كجزء صغير من مسار كبير في المستوى المركب. تاني حاجة بنختار شكل المسار ده بذكاء عشان يسهل علينا الحسابات. تالت حاجة بنستخدم نظريات كوشي العبقرية عشان يلاقي قيمة التكامل على المسار الكبير ده كله، وغالباً بتكون سهلة جداً. وفي الآخر وبشكل يكاد يكون سحري، النتيجة اللي بنوصلها دي بتدينا حل التكامل الحقيقي الأصلي اللي كنا محتارين فيه.
والأفكار دي على فكرة مش مجرد حاجات نظرية في الكتب، دي حرفياً حجر الأساس اللي قايم عليه فروع كاملة في الفيزياء والهندسة. بنتكلم عن ديناميكا المواقع، حسابات الجهد الكهربي في الكهروستاتيكا، حل معادلات انتقال الحرارة، وحتى تحليل الإشارات في عالم الاتصالات. كل دي تطبيقات بتعتمد بشكل مباشر على المبادئ القوية دي.
في النهاية الرحلة دي بتورينا حاجة مهمة قوي. ساعات عشان نفهم الواقع المعقد اللي حوالينا لازم يكون عندنا الجرأة إننا ندخل عالم الخيال، عالم مجرد زي المستوى المركب. ولما بنعمل كده بنكتشف إن الواقع نفسه بقى أبسط وأوضح. والسؤال اللي بيفضل معانا هو يا ترى إيه كمان في حياتنا ممكن يبان صعب ومعقد النهاردة، وممكن يبقى بسيط جدا لو بس اتجرأنا نفكر فيه بشكل مختلف.